Okay, we are live on our first Fluent live stream. This will be very fun. We've got me, I'll kind of moderate the thing, Dino, one of the co-founders, and we got Dimitri, co-founder and CTO of Fluent, got Steph, Fluent COO, and then our two favorite defenders of blockchain and L2 architecture and communications, Toggle from Scroll and Luca from L2 Beat. Thanks for coming on, guys. So to start, let me just give. So this is going to be like a session of just unpacking blended execution from kind of a technical perspective. We have been talking a decent amount over the past couple of weeks about the kind of like high level idea and like what kind of developers and users get, but it's time we kind of like dive into some of the details. So have these guys on and we'll just have like a free flow conversation to dig into it. And just to kind of like set the stage, high level blended execution is a kind of an architecture where like one state machine can support kind of apps from multiple different VM targets. Fluent is, for anybody kind of new to this, specifically focused on WASM, EVM, and SVM apps. And the idea is for each of these apps to be kind of like first-class citizens of the network, and for each of those apps to be able to directly kind of call each other. And I guess just to, inform anybody who's kind of new to the idea, but I'll stop there. Welcome, guys. Feel free to dig in.
Yeah, so thanks, Dino. So like usually at my work, I read a lot of Solidity contracts, right? Like I review all these projects, lots of thousands and thousands of lines read. Does this mean that now when you deploy Fluent on mainnet, I will need to review, I don't know, Rust contracts, like Rust pre-deploys on Fluent, just as the security of your system?
You sound very excited about it. Not sure if you're saying it as a good or a bad thing.
I don't know. Just asking.
So I can answer. I will try to go not super technical. I want to make it fully understandable for everyone. For developers, for developer experience, if you're an Ethereum developer, for you nothing changed. The way how you used to deploy application in the past will stay the same for Fluent as well. And the only difference that really makes sense is now we are able to run Rust contracts. Not only Rust contracts, but also maybe C, C++, etc., any language you want. The only requirement is this language must be compiled to WebAssembly. And for the simplicity of understanding, it really feels like a precompile. For example, in Ethereum, all Solidity developers know such precompiles like EC recovers, etc. And it's almost the same. You can develop your own small precompile using any language you want. For example, Rust. It's a very good example. And you can deploy this precompile and invoke functions and interact with this application and get results. So any sort of resources required computations where your stack size is very limited, you want to expand the computations, you want to do more. So here, this is the solution, and it can solve your problems.
But like, I understand Solidity is a language that is written like specifically to interact with a blockchain, right? But Rust and other languages are not. So like, is it correct to say that like can you use like Rust as it is, or like do you need to remove like some of the functionality, for example, from these languages?
So the first requirement is your application cannot use any operating system features. Like you cannot read files, for example, because it makes no sense for blockchain to allow developers to use files. You cannot access network directly. The only thing you can use is blockchain specific environment. So the environment that we provide for developers. And for if you're developing your application using Rust, in terms of Rust, there is no limitations. Everything you can run and develop using Rust, you can do the same on Fluent. There is no any major difference in this case.
Like, what are the, how do you access, like, for example, how do you specify if something is like a storage variable or a memory variable?
Mhm.
Like, how
So
do you interact with the underlying um,
yeah,
machine,
so
the
uh,
blockchain?
yeah. So to solve this, we provide for developers a set of special functions. We call them bindings or host functions, and these functions are used to access uh, for example, storage. Actually, you don't access storage; you access operations under your state tree. But let's call it storage. So you can call a special function that modifies storage for your specific address, and you can store some elements. This is absolutely the same how it works and feels in Ethereum, for example, in Solidity. You create a mapping or a variable with some data, and you can put some information, you can delete some information, read information. So for developers, it's absolutely the same. And technically, there is no difference what language you use to access storage. You can use storage keyword in Solidity, and we are providing the same keyword. And it's also called storage. So you just create a special variable with a special keyword, and you can access elements and store them persistently inside the state tree. And regarding the storage, one thing I want to highlight that uh, uh, we have, since blended execution supposed to have and support different execution environments, you can choose any uh, execution environment standard you want to access storage. For example, you're creating Rust application, so just Rust application, and you're not binded to any specific EVM standards, Solana standards, or all other standards. And if you want your application to behave like EVM application, you can use our special execution environments adapters like precompiles, and these precompiles can help you to simulate the same standards as, for example, Ethereum have, or for example, Solana has.
Okay, I guess I'll jump then. Uh, First of all, I wanted to ask a very important question. When are you gonna have a fight on Twitter about whether you're actually a first blended execution environment or not? That's the most important thing. I'm just like getting flashbacks to the first EVM fight. So I'm like, are you gonna have the same with someone?
Depends who wants to get in the. I mean, who wants to get in the ring? Come on in.
I don't know. I'll stay away from this one for now. But jokes aside, so basically the as far as I understand, the underlying execution layer is actually WASM, and then you can support EVM or other VMs. From what I understand, Arbitrum is doing something similar with Stylus. What are the main differences here, or are they similar approaches?
Yeah, very good, a very important question. So the thing is, I, I I want to go even further and do the comparison with all multi-VM approaches, because the problem when you take one VM and you connect another VM to this VM, you must have something like a joint between these two VMs, because you need to find a way how they can interact. They use different standards to access storage tree. They can even have different trees inside. For example, Solana uses different cryptography, and you cannot access the same elements in state using Solana addresses because they're produced using different hash functions, different cryptography. It's impossible. You cannot find collisions there inside. Otherwise, all of the security will be revealed. And this is the biggest difference comparing to multi-VM approach and blended execution approach. In multi-VM, you must have some sort of precompiles, helpers, adapters, something that can describe how you can access another VM. And it feels like a bridge. And you cannot interact with, for example, these contracts directly. You must go to a special precompile and ask, hey, could you please send a message? And your storages are not interoperable. It doesn't persist in the same tree. And also your accounts are different. And here the biggest difference is in blended execution, you have only one state and you have only one tree. It means that no matter how your application is deployed, developed, is executed, you all the time exist in the same tree. So there is no need to have any additional precompiles, adapters, bridges, edges, joins, and all other these things, because you can directly interact with applications that are developed using different address format, different cryptography, and etc. I can go deeper technically and explain how it works, but I think it's not super important right now.
So just so I understood it correctly, in this approach, a contract written, let's say for SVM, can access the state of a contract written for EVM without going through any adapters or like any bridges or like going from like one state root to another state root, right?
If you mean accessing storage directly, so you need to initiate an invocation of the contract. So
Yeah,
you
yeah,
need contract, of course, yes,
of course,
somehow.
yeah, yeah.
And a contract, it provides functions that can be used to fetch information from the storage,
Yeah.
from the state tree. So yes, it's full right.
Cool, makes sense.
Dimitri, could you maybe touch on like what that looks like as a user? Like, let's say you have you're using an SVM based app, and then you want to move over and start using an EVM based app. Like, what does that actually look like? Like, how many steps are you taking? Like you mentioned that there's no bridges, so what does that look like for a user?
Yeah. So let's say let's assume we have only two execution environments, EVM and SVM. So EVM or SVM. So I think this is the best example of interoperability between these two platforms because they're entirely different. They different cryptography, Edwards curves versus SEC256K1 curve, and etc. Different hash functions, even different private key format, how they're getting derived, and of course, different transaction structure. That is also very important. And if you have a developer from EVM space, and developer can interact with Fluent natively. So for a developer think that he works with regular EVM chain because it supports EVM, it supports all functions. It has no any additional. It brings no any additional limitations to the execution environment. It feels like EVM. And the same happened with Solidity developer. Solidity developer also think that he behaves with SVM chain, with SVM compatible chain, because he used the same extension, the same wallet, and upload the same transaction. But the difference is that they technically exist in the same space. So there is no difference between them because they think that their environments are different, but it's the same environment. And they can do the following. They can, for example, transfer assets natively from EVM account to SVM account to SVM user. So EVM user just takes SVM address from his friend, for example, and just send him his native assets without any bridges, any wrappers. Nothing is needed. So you just simple send, and it works. The same happens with, for example, with running smart contracts. For example, if there is a contract that is written on Solana, EVM developer can just invoke this contract and get result. And here, okay, I will highlight this problem a bit later, but there are several potential tiny tricky cases, scenarios that can happen in this case. But I think we have answers on all these possible corner cases.
So one thing I'm wondering, if you want to support, I don't want to say VM because in this case is not the correct way, but like languages targeting different VMs inside this framework, do you have to whitelist the VM? I don't know how to refer to it, the VM emulation contract for that specific VM, or is it permissionless? I can support any VM.
So
I can integrate any VM.
Yeah, so very good question. What's your referring? We call it compatibility contracts. So it's technically precompiles this persistent genesis, but we call them compatibility contracts. Technically you can. Technically, you can deploy your own precompile, but right now we disallow this because it requires a lot of permissions to be granted to developers, because they literally can access the state tree, and by having access to the state tree, they can modify leaves, and it can cause modification of balances. So right now, all of these compatibility contracts are fully trusted and developed and validated and verified by us. So right now, only Fluent can enable new VMs. But theoretically, I don't see any limitations with providing special SDK where developers can develop their own compatibility contracts and bring support of any execution environment they want.
And I guess I would just add that in addition to deploying the L2, Fluent's also building the Fluent-based framework, and so even if the L2 will only support EVM, WASM, and SVM apps, like just to start, like that doesn't like disincentivize anyone else from being able to contribute to the framework or work with us to be able to support additional VMs. And we have been talking to some teams that want to get in on the blending, and so we're hoping to see different teams deploying different blended execution environments that have different VMs that perhaps we're doing for the L2, and there's a lot of customizability there.
So in other words, you want another SDK that acts as a graveyard for dying L1s. No, I'm joking. There are actually cool stuff being built like with SDKs, but in general, I think right now, in a lot of cases, it's just a graveyard for dying L1s.
How does the transaction pricing mechanism work?
You mean the price, the gas price, and gas calculations for the transaction? Oh, yeah. So, super cool question. I didn't expect this question, but no worries, I have an answer. So the problem is if you execute EVM transaction, there is a standardized way to calculate gas, and it's not correct for us because we use WebAssembly instruction set. We actually use reduced WebAssembly instruction set. So we have our own instructions and we have our own gas metering. So we cannot execute EVM instructions according to their official specifications because it's not technically correct for us. Of course we can, but the problem is that since we're ZK rollup, we're limited with proof computation time, and it also depends strictly on the instructions used to compute the proof. Because in the real world, in the real CPU world, instruction execution time is not the same as in ZK proving world. So you can have, and some instructions instructions are really friendly for ZK computations, and some instructions are very friendly for CPU computations. And everything we have today in Ethereum standards, they are used to all the standards were calculated for CPU execution. They are not aligned with the ZK proving process, and this is why we technically can use Ethereum gas standards, but we at the same time cannot. So we're going to have our own gas in our system that use WebAssembly instructions to calculate the price of the transaction. And according to our current benchmarks, price will be a bit cheaper than in EVM transactions, or at least the same, very similar.
Just to understand, does that mean that the gas schedule for me building a Solidity contract for EVM will not be the same as an EVM? So let's say if I have a call with a pre-allocated amount of gas to that call, that might not work in this case. Let's say if for some reason the underlying gas schedule makes it more expensive to make that call.
So it theoretically can happen only if our gas computation is more expensive comparing to EVM. But according to our benchmarks, it's going to be less than EVM default gas policy.
Okay, so but is it less for every opcode, or are there exceptions?
Uh, I don't know how to map all the subcodes. It's a really hard task
Yeah, of course, of course.
to map all EVM opcodes into WebAssembly opcodes in time. But I think we will keep all prices for our EVM instructions less, or at least the same as original EVM instructions, because it refers to the way how we optimize execution. If you're interested, I can explain. This is very interesting. Why we have less gas comparing to EVM? The answer is very simple, because we do not simulate environment. We do not run any VM inside. This is not true. Okay, so I lied all the time. We don't have multi-VM. We don't have different VMs. We have only one VM inside. Our first citizen is RWASM, is reduced WebAssembly. And it is used to execute only RWASM instructions. We don't know. Actually, we don't care about EVM and all these standards, because we do ahead of time translation once the application is deployed. And we translate and reduce. We do the reduction process of the application into our intermediate representation language. And this language is used to prove the transition. And since we don't do simulation, we can do several WebAssembly related optimization technique related to, for example, how we manage heap base, how we manage stack elements, and we can do a lot of things much cheaper comparing to how it works in EVM. Since for us, there is no technical need to simulate the entire environment, we can remove unnecessary things, and by keeping the same or less execution cost.
But, I think this is the correct approach. Like, I know many ZKVMs that misprice opcodes because they want to remain compatible. I think Scroll is an example of this, right? That you want to return
Why
the
am
same.
why am I on the receiving end of strays here? Like, I didn't do
Come on,
anything.
come on. No, but like
Yeah, but I'll explain
like
the reasoning why. The reasoning is that long-term proving is going to be so cheap that it doesn't matter whether the opcodes are mispriced or not.
okay, interesting approach. Okay, I don't want to go into the Scroll details, but um, I don't feel like I'm not a developer, so probably I'm wrong. But I don't feel like that mispricing opcode, not mispricing, but having different pricing for opcodes is not much of an issue for applications.
I think as long as they're cheaper, it's fine. My concern is if they're more expensive, because let's say if by default Ethereum Solidity compiler allocates what 2,100 gas to a call if you don't define how much gas you want to allocate in a custom way. So like if it's actually more expensive, then it becomes a problem. But if it's cheaper, then it doesn't matter, I think.
Did we just lose Dimitri?
He was like, "That's it, guys. I'm bored with your basic questions."
He's get. Oh, there we go. Hey, man.
Somehow I have been dropped. I don't know why.
DDoS. It's
Yeah.
all DDoS.
It turned into a scroll stream. Somehow Toggle always gets pulled back in the ring. Like he just finds his way there no matter what.
Yeah. Talking about DDoS, by the way, does having support for multiple 3M targets, let's call it this way, does it increase proving cost and like decrease proving efficiency, or it has no impact on proving?
Mostly it has no impact because, yes, as I mentioned, we do reduction of all instructions into our reduced instruction set. So for in terms of proving, there is no difference what application you execute. Of course, theoretically, if there is an additional overhead, for example, you develop a function that calculates a sum of three numbers, of three 46-bit size numbers. It is friendly to WebAssembly. You can do the following using SVM, and you can do the following using EVM. But EVM always align your stack with 256-bit elements. So for the solution, so the program is the same. It's just developed using different languages. But of course, on SVM or WebAssembly, it will be much faster because it doesn't use big computations.
And because the reason why I was asking it is because, as you mentioned before, you need compatibility contracts for every VM that you support. And I was thinking whether having that is such a precompile adds overhead to when you actually compute proofs for like Solidity contracts or Rust contracts that were written for EVM and SVM.
Yeah, agree. Technically, it's true because if developer, all these execution environment precompiles are not required for developers. It's not mandatory for developers to use these precompiles. They only if they want to support strictly all, for example, EVM standards, and they want to create an application that behaves like EVM, but it's written using Rust. It uses the same, for example, instructions. It behaves. It can do delegate calls and execute exactly the same behavior. In this case, it can bring additional overhead into WebAssembly computation. So because it's much easier for you to do if you develop application using WebAssembly, you can just invoke WebAssembly contracts. You can develop everything according to any API model you want. You can encode, decode everything you want. So you can go with with the most optimized approach you want. But if you want some way to be compatible with Solidity APIs, you want to be compatible, for example, with EVM call semantics, then of course you bring this additional overhead to your application because you need to run simulation of the execution environment. You need to create all these structures in the memory.
How does the call data would look like? Like the not call data, like data availability.
Yeah. Even the call data or data will be. Oh yes. Okay.
I mean, how do you post data to Ethereum?
So this is the good question. I'm looking for the best words to describe. So the problem is that in EVM there is no any type of API encoding standards. These standards exist in Solidity. So when you create so-called call data, you actually use Solidity standards, because Ethereum itself, it doesn't describe any standards for execution environment, for input output encoding. There is no standards for this. All these standards are driven by Solidity, and of course most of developers, okay, I can say 95% of developers support Solidity API compatible standards for passing call data. And we are developing virtual machine. So it is the same as EVM. If EVM theoretically cares about API, it doesn't care about API, why we should care about API? Because it's an upper level problem. It doesn't touch EVM directly. And the solution for us, so of course, we are not going to provide inefficient experience for developers. We are trying to make the transition very smooth for developers and very understandable. So of course, we are going to provide libraries that they can use to create fully Solidity API compatible inputs, outputs, decodings. So all these toolings are already developed, and developers can use it. And if they want to go with more optimized solution, they can use different API scheme. For example, in Solana, you can use any API scheme you want. There is no any direct standard. You can use Borscht encoding. You can use just little endian binary encoding. You can use any encoding scheme. And a lot of developers ask me, so if there is no standard, how all these developers supposed to interact to each other? Because there is no standard. But when you're developing a Solidity application, do you think there is no standard? There is standard. But when you create when you want to invoke another Solidity contract, you create a special interface with a list of all methods inside. So you specify standard to interact, and you can do the same. It doesn't have to be Solidity API. It can be different scheme. And all these methods are used to encode using Solidity directly. So we can create a library, and you can just use this library to encode API calls in any way you want. And we're fully, we don't want to break developer experience. We want to expand developer experience to keep compatibility with all the existing tooling and existing standards, and expand it with more WebAssembly friendly and WebAssembly optimized standards.
A bit of a different question. Let's put it this way. I'm a bit of an Ethereum OG, so I still use my Mist wallet when transacting with Ethereum. Can I use my Mist wallet when transacting with Fluent or no?
Yes, why not? You can use your Mist wallet, and you can deploy. You just take your application, you encode it into hex, and insert into your Mist wallet, and send the transaction. Right now, so there is a thing that right now we have after detection for input binary, and we automatically decide how to do the translation. We check that collision shouldn't happen. There is a very interesting contract where collision can happen, but it makes no sense to develop such contract. It's fully useless. But we thought that it can be nice for developers to use different deployers, for example. So once you deploy application, you can just put special address and say, hey, I want my application to be deployed using this special deployer. And the deployer is used to translate the application from WebAssembly to RWAS. And it expands significantly the developer experience, because now you can deploy your applications using MetaMask that before wasn't possible at all. It's a joke. Not about MetaMask, but
Okay, so I think that's actually like a good segue. There were some questions that we gathered over the past week from people on Twitter. So I'm gonna run through. Steph and I can like run through those. And one is related to actually wallets. So Noah from NodeKit was asking, and we touched on this a little bit earlier, but I think it'd be good to dig in further. So put yourself in the shoes of a user. Like, can I use the same wallet like across these environments? How does my experience as a user change for the different environments I want to use adapt? So it's like, cool, we could deploy EVM apps, SVM apps, WASM apps, but I'm a user. Like, I don't care. I just want to use whatever apps are on there. I don't care how it's written. What's my experience like?
Yeah. So your experience is the same. There is no difference. You can use your MetaMask wallet. You can use any other wallets to access Web3 features, because the environment is fully Web3 ETH namespace compatible. So everything that is developed and designed for EVM tooling, you can use. The same works for SVM. Since all RPC methods are supported, you can invoke, you can use any Solana tooling. So in terms of developer experience, there is no difference. Difference appear when you start to work on the edge between these two execution environments. So-called third execution environment, we call it, I don't know, fluent, blended, I don't know. And using this execution environment, you can do magic things. You can combine, you can build product that uses, for example, ERC20 tokens and SPL tokens at the same time. And you can combine logic in these two different languages. Yeah, so we're still locked on this comparison between EVM standards and SVM standards, but technically, there is no limitation how many execution environments we can support. We can add support of anything, because it's just an application that's developed using Rust. So if it's compilable to WebAssembly, we can support this execution environment. Of course, yes, we apply several optimizations, because if you take original EVM and compile it to WebAssembly, it will be very expensive. So you need to do several optimizations, and then, of course, it will be super fast and amazing.
Can you maybe walk through, like, I'm a Solana wallet user, so I'm using Phantom or something like that, but I'm going to be interacting with, let's say, like a Uniswap fork, so an EVM app. What does that look like for me?
For you, if you want to interact with Uniswap through Solana, it can feel a bit strange, because it can even be a bit confusing. Yes, you can do this. You can do this. It's a bit confusing, but you can do this. Why it's confusing? Because Solana is designed to work. Solana wallets and extensions are designed to work only with Solana compatible addresses. But I think that Uniswap uses Solidity and uses EVM addresses. So addresses are different. And in this case, you need to calculate a special address for your Solana wallet to execute Uniswap, because to execute trade. Because technically, you need just to take it was here, yes. You need to take EVM address of Uniswap, translate it to a special Solana notion, and then you can interact with this application. And I promise you that once you send money or call trade for this application, the result will be 100% the same if, for example, you interact with EVM application. Because if we look into the tree, address is just the way how you access your account, how you access your leaf. And you can calculate and you can use any representation for the path inside tree you want. You can use Solana path, you can use EVM path, but under the hood, the contract is the same. So you can calculate a projection of the address for your Solana wallet. And you can do, for example, the same with your personal wallet, and etc.
All right, going to transition to another question from the audience. Looks like this one's from Getz. Getz asks, are there any performance benefits or sacrifices versus running the VMs natively? I think we kind of touched on this, but I think we can dive in deeper as well.
Yeah, so There is a difference. As I explained before, it's faster because we do ahead of time translation. Deployment process can be more expensive, uh, several times more expensive, but execution is much faster. And the biggest idea we have is uh, we use this ahead of time compilers, and we use this RWAS execution environment. It's important because, for example, right now our execution environment is stack based, and if we find that it's better to go to with register based approach for our virtual machine, we can just do this. And all applications that are translated since this time point, they will have more optimized applications. And this is how we can balance between, for example, ZK proving time with execution optimizations and etc. And also, one important thing comparing in terms of performance, we have so-called circuit extensions, and we provide these extensions for developers to interact with low-level features. For example, you can interact with some hash functions, with Pseudon hash functions, with Kitchak hash functions, etc. All this development-related stuff. And we can replace these hash functions, for example, with our circuits and speed up proving process in this scenario. So this is how we achieve better performance by doing more work during the deployment process. Yes, we need to do translation, but afterwards we have better performance for the runtime and for execution.
Actually, I have a question that came to mind and has been brought up a number of different times, right? Like we're talking about SVM, talking about blending these different environments together, but clearly when people hear like EVM and people hear SVM in the same sentence, they're like, oh, okay, well, like what happens with the whole parallelization feature? And I know like this is kind of maybe a discussion that even Toggle, like you might want to jump into, because I know you've done a lot of like research over the past year on parallelization. So the question is like how does parallelization of any of these environments tie into like a blended VM? Like, do we lose SVM parallelization? Can you get EVM parallelization? Like, how exactly is this enabled, if at all?
Yeah, there are different ways how we can achieve this. SVM achieves parallelization due to the transaction structure. EVM has more optimistic approach, and it theoretically can support parallelization if it enables strict access lists. So we can, for example, combine these two solutions and use SVM pre-calculated dependency traces graphs, and also use strict access lists in Ethereum transactions to use parallel execution for these transactions for block execution. From our perspective, we don't see any restrictions and any limitations in running parallel execution. We also can anytime go with optimistic approach for parallelizing transactions, and it's still possible to support no matter what layer is used, for example, SVM or AVM or any of those layers.
I'll just concur with that and add that like when people think that like there's something special about SVM that allows it to be parallelized, or like something special about EVM that makes it impossible to parallelize, that's like not true. You can parallelize any VM, or you can make any VM sequential. I can like remove the Solana scheduler tomorrow and make it sequential, and I can change the Ethereum scheduler tomorrow and make it parallelized. So I think they're just different approaches to parallelization, and yeah.
So how do one quick follow-up, and then Steph, maybe you can finish out the last like two questions that we had. So like what's our thinking, Dimitri? Like, are we, if we enable parallelization like on the like RWASM level, and then like do we want to support kind of parallelization for each of the different VM targets we support? Like, is that part of our plan?
If we want to have parallelization, then we all the time must support parallelization for all execution formats, because parallelization is more about transaction format. And even if we use the same state, so we can do so-called like prediction for state transition and check what slots and leaves are affected inside tree and use it to parallel execution. And yes, definitely we want to go with parallel execution, but it's still, yes, work in progress, and a lot of work has had to be done before this.
All right, next up is a question from our friend Nash, researcher at Celestia. He asks, how are we going to deal with sequencer proposer failure, aka how are we going to do force withdrawals?
Yeah. Good question, as always. So I think the optimal solution is to have emergency withdrawals. So because why? Because it can be used for both pure ZK and optimistic ZK, for example, approaches. And also, if there is no, for example, new blocks or events from between layer 1 and layer 2 for a significant period of time, for example, for 2 weeks, then it can be used to withdraw funds from that are locked inside contract. It's not the best solution because in this case, some assets can be locked, for example, inside some smart contracts, for example, inside Fluent. So to prevent this, we're integrating with different DA layers, and we use them to store data availability data. And theoretically, they can reconstruct, they can collect all DA data, all call data, from our layer and reconstruct the block and commit block on themselves. And for example, to execute, to make a withdrawal from some contract to unlock their funds, and then to do the emergency withdrawal or to initiate instant withdrawal from our protocol.
Actually, I want to jump in and see Toggle, Luca. Like, this is something you guys obviously think a lot about as well. And we're early enough in like the journey where we're thinking through different options, such as what Dimitri mentioned. But like, what do you think's ideal?
I'll start by saying one thing. I don't like the term forced withdrawals because I don't. I'm really skeptical about it even possible for you to implement forced withdrawals on a chain with general purpose computation. I like when people refer to it as forced inclusion. That's much easier to do. I think the problem with forced inclusion, especially for ZK VMs, is the fact that you can trivially force include an invalid transaction, for example. So your proof system has to be able to handle proving invalid statements, so invalid computation. So basically, like if you produce an input that produces an invalid output, your proof will just basically output the same state as as was inputted into the proof, and just say that everything else, all the computation was invalid. And but that adds overhead. So I think that's where we're not seeing as much forced inclusion being done, work done right now on the side of ZK rollups, because it's just not very optimal at the moment. But I think like the approach is this. I think the optimal approach for a ZK rollup is to add the functionality to the prover and to be able to prove invalid statements, and then just add forced inclusion.
Yeah, I can confirm that all ZK rollups have this same problem, that they cannot prove invalid data. But let's say that this gets solved. You have two options. The first one is to have like a centralized sequencer and a mechanism to bypass the sequencer to like sequence transactions yourself. Or you have a base sequencing. But in a way or the other, you need to like go through 12 L1 to push transaction to inherit liveness and censorship resistance of Ethereum. So yeah, I mean, forced exits in the same way that you have like escape hatches in DYDX or zkSync Lite do not really work for generalized VMs. Like we tried to do this with Plasma for a long time, and we didn't manage to. So yeah, like the way that you implement forced exits in practice is that you will implement forced transactions, like forced inclusion in the L2, and then a mechanism to like self-prove the state transition given the inputs that you like self-sequenced.
All right, last question of the day, unless you guys have any others, also from Nash. I guess also, Dino, this one's for you and Dimitri. If you already blend all VMs on the L2, is there still a need for L3s at all?
So I'll jump in and take this real quick, and then Dimitri can shed some light on it too. I'm actually gonna broaden the question to like L3s or like other L2s or just other chains in general, and because it's like a natural question, right? Like, okay, we're saying, oh, all the apps can just sit here, so are should they all just go there, and then there's no need for any other rollups? Like that's not how we see it. Like there's like always trade-offs, and like for example, we're making a trade-off of starting with a focus on EVM, WASM, and SVM, and like we just talked about, and so clearly there are other VM targets that somebody can focus on and then like optimize for. Like theoretically, like I mean, we just talked about whether like our plans for parallelizing the environments. Well, like that is a trade-off. Like we can parallelize it or we cannot. And so like I think like those are some obvious like tech trade-offs, and I think that people will make all different ones. Like we're obviously also focusing the environment on like being very EVM compatible. Some people might choose not to do that, and then there's like all other sorts of like trade-offs and customizations that still come into play, be it like privacy or be it even economic or governance models, all in sector focus, whatever it might be. So we definitely see like a future of a bunch of different, hopefully blended execution networks, which is why we're building the Fluent-based framework alongside with Fluent L2. And so this applies to L2s, L3s, whatever. Dimitri, so I know you maybe want to shed more light on kind of specifically the L3 thing, because I think we have a pretty novel construction there.
Yeah, so I don't like the word L3 because when we talk about L3, you strictly limits developers with developing some sort of chains. But what if they want to develop something different? Why? For me, the term L3 forces developers to develop side chains, and uh, we want to use a bit slightly different naming here. We call it dedicated applications or sovereign applications. And the idea is that you can outsource computations, for example, to your personal environment or to someone's environment, and don't execute it directly inside our state. So you can use your personal state, and you can use any sort of computations. You can run an exchange, you can run a blockchain, you can run a funny game and do some off-chain logic computations, and then you can just prove it using, for example, some computation marketplace, and include this proof into our aggregator. Let's call it aggregator, and our aggregator collects all these proofs and aggregates them together, and it settles all changes into, for example, layer one in the final aggregated proof. And in this case, developers are not locked with developing only, for example, layer 3, because they can develop any apps they want and just run it independently from our state on their personal state. If they want to have some sort of, I don't know, optimizations, if they want to run parallel execution, or they don't want to rely on the shared state at all. So this is how we see it.
Awesome. Well, I know we're coming up on the hour. And that was all the questions we had from the audience. Toggle, Luca, if you guys are good, I think we can wrap up.
I'm good.
Okay, cool. All right. Well, thank you everyone who's made it this far listening. Appreciate it. Hopefully you learned a thing or two about blended execution. We'll be having more of these hopefully over the coming like month or two. So stay tuned, and thank you Toggle and Luca for joining us as well. This was great.
Thanks for having me.
Thanks as well.
Thanks, guys.
Cheers, guys.
Bye, guys.
Yeah.